What we're going to talk about here is the first modification that can be made to these oscillating or simple harmonic system, and that's damping. Damping, to put it very, very simply, all it really means is we're losing either energy or something else to the environment. And what this loss of energy or other things to the environment is going to do is it's slowly going to reduce the amplitude of our oscillations. Now, mathematically speaking, again, we're not going to go through this in painstaking detail because it requires solutions to differential equations. But what you'll notice is the oscillatory equation that you'll see here. I'll box it off in red. There's an extra term present in it that affects the amplitude, or the overall size of it as time increases. And that's simply this negative exponential here. This negative exponential here can also be written with an exponential function, so an exp function. But regardless, what it does is it basically steals your oscillations over time. Now, when it comes to stealing these oscillations over time, there's two ways that I can go about doing this. The first is an overdamped case. So normally what you would have here is you'd have, some nice oscillations going back and forth. In the overdamped case, which we're going to put in blue, what happens is these oscillations get stolen so quickly that you don't see any overall oscillations at all. So this is the overdamped case. In other words, things are being taken from you so quickly that it basically kills any vibration back and forth that you'll see. And you can demonstrate this if you grab something connected to the end of the string, swing it back and forth like a pendulum, and then you grab it with your hand and stop it. You have effectively overdamped the system because you have stolen all the energy more quickly than it can be used to oscillate the system back and forth. The second type of damping, which is the one that is actually present in the equation on your screen, because it's the only one we're realistically going to talk about, is the underdamped case. What this means is the system is allowed to oscillate back and forth, but as you steal energy from it, the oscillations get weaker and weaker and weaker until they die out. Right, so this is known as underdamped. And the underdamped case in most systems is usually the more likely one. Overdamped usually requires significant external intervention. In the overdamped case, if you wanted to model this mathematically, you would just get rid of the oscillatory component, and that's a reasonable approximation to it. Again, we're not going to go super into the mathematics of it because it's well beyond the scope of this particular version of Physics 1. Now, with that being said, you can see this in a number of different situations. Basically, this is going to happen anytime you have some kind of oscillatory function that's getting interrupted by a loss of energy or by a loss due to the environment. Now, in terms of finding these in practical application, one place that they're quite common is actually dealing with MRI systems or NMR systems if you were in chemistry. One of the general ideas here is when you go to actually have an MRI picture here, one of the important characteristics that they look at to map out the MRI are the T1 and T2 relaxation times. In other words, these relaxation times are directly related to damping coefficients. So what you'll see here, generally speaking, you don't have to worry too much about the pulse structure of this. I'm not here to teach a class in MRI. But the idea is if you send in an exciting magnetic pulse, it creates a very big oscillation at the start. So you're, somewhere up here. And as time goes on, the signal relaxes itself down. And by measuring these relaxation times, it gives you important information about the thing that you're looking at. And so when you're looking at systems like this, what you might see is an actual map of these T1 or T2 relaxation times. So this idea of a damped system shows up in a lot of different applications. And in most real systems, there will be some damping present because most systems are not completely isolated from the environment. And if you're doing the lab that deals with motion, one of the parts of the lab deals with that explicitly. So it doesn't really matter if it's something like an MRI pulse or something like a spring or a pendulum you're vibrating back and forth. If it is losing energy to the environment, its oscillations around its equilibrium point will eventually slow down and stop, simply because the energy is escaping to the environment. If you want a technical term to it, in physics we refer to this as an open system because it's open to the environment.